In the previous video series, we explained that for nearly 50 years, Voyager 1 and Voyager 2 have been traveling beyond the edge of our solar system, sending back data no one thought possible with 1970s technology. But now, scientists are proposing a new mission, Voyager 3. Unlike its predecessors, it would be built with modern instruments, AI navigation, and longer-lasting power systems designed specifically to study the interstellar medium. In this video, we'll look at why researchers believe the time is right, what Voyager 3 could reveal, and how it might prepare us for future journeys beyond the heliosphere. Voyager 1 and Voyager 2 launched in 1977, taking advantage of a rare planetary alignment that occurs only once every 175 years. Using gravitational assists, they visited Jupiter, Saturn, Uranus, and Neptune, returning images and data that transformed planetary science. Active volcanoes on Io, intricate ring systems, and strange moons like Triton and Enceladus reshaped our understanding of the outer solar system. Once their planetary missions ended, the Voyagers kept going. Voyager 1 is now more than 24 billion kilometers away, the most distant human-made object, while Voyager 2 trails only slightly behind. Both have crossed into interstellar space where the solar wind fades and galactic plasma dominates. But here's the challenge. The Voyagers were never designed for this. Their plasma detectors are limited. Their magnetometers lack resolution. And their data trickles home through faint transmitters. Each year, engineers shut down more systems to conserve what little power remains. This is where the case for Voyager 3 becomes clear. A modern probe could be built with instruments specifically tailored to the interstellar medium, measuring plasma density, charting cosmic ray fluctuations, and mapping magnetic fields at far higher resolution. With AI-based navigation, it could adapt autonomously to unexpected conditions. With improved nuclear power systems, it could operate long after the original Voyagers fall silent. In essence, it would not just extend a legacy, it would begin a true exploration of the region the Voyagers only glimpse. Why is studying the interstellar medium so critical? Because it is the environment our solar system constantly moves through. The sun's solar wind creates the heliosphere, a vast bubble that shields Earth and the planets from much of the galaxy's radiation. But its true structure remains uncertain. Is it a long teardrop trailing behind the sun, a compact sphere, or something in between? Voyager 1 and 2 provided the first hints, but their data is sparse. Voyager 3 could fill in the gaps. With modern detectors, it could measure plasma density at fine resolution, track how cosmic rays penetrate the heliosphere, and map magnetic field variations across boundary layers. These insights would refine models of how our solar system interacts with the Milky Way. There are also practical reasons. Understanding radiation and plasma conditions is essential for designing future spacecraft, especially if humanity ever attempts interstellar travel. Regions of calm or turbulence could influence shielding requirements and navigation strategies. Just as ocean currents shape the routes of early explorers, patterns in interstellar plasma may one day guide missions to nearby stars. On the theoretical side, Voyager 3 could test competing ideas about cosmic ray transport and magnetic field structures. Observations of galactic radiation gradients, particle acceleration, and boundary turbulence would allow scientists to compare data directly with astrophysical models. In this way, it would bridge theory and observation, turning speculation into evidence. By doing so, it would not only answer questions about our local environment, but also inform astrophysics more broadly, linking the small-scale plasma around the Sun to processes across the galaxy. The significance of Voyager 3 extends far beyond data tables. Practically, it would act as a pathfinder. Just as early maps charted seas and currents, it could create the first detailed atlas of interstellar space near the Sun. This would not only guide scientific understanding but also provide critical information for engineers planning future robotic or even crewed missions beyond the solar system. Culturally, it could continue a tradition begun in 1977 with the Golden Record. The original discs carried sounds, music, and images of Earth as a message to any civilization that might encounter them. Today, a new archive could be digital, containing art, literature, scientific knowledge, and perhaps AI-generated messages crafted to communicate without language barriers. It would be both a scientific payload and a cultural time capsule reflecting who we are in the 21st century. Timing adds urgency. The Voyagers benefited from the last great planetary alignment. Similar configurations which enable slingshot maneuvers for speed will occur again in the coming decades. But missing them could mean delaying such a mission for a lifetime. For many scientists, this makes the case clear. If humanity wants to send a true interstellar probe soon, the opportunity must be seized. Meanwhile, NASA and other space agencies are studying related concepts. One prominent idea is the Interstellar probe, a proposed mission that could launch in the 2030s or 2040s and travel far faster than Voyager, reaching the heliopause in about 15 years. A Voyager 3 mission could either complement or evolve into such efforts, ensuring continuity between past achievements and future exploration. Together, these arguments highlight why scientists see it as more than nostalgia. It would be a step forward, practical, cultural, and symbolic. Voyager 3 wouldn't just repeat 1977. It would push deeper into interstellar space, refining science, testing future missions, and carrying humanity's story to the stars. The first Voyagers became our messengers. This one could be our new voice beyond the sun. Shouldn't we launch it? Are we ready to launch humanity's next great journey?